now.
Full screen. Okay, great. Hi everybody, my name is Julia, and I'm a research scientist at Skoltech, working at the laboratory of Professor Chuhotsky, and also collaborate closely with Ivan Selidis. And today I will make a brief introduction to the audio processing, and namely, I will talk about the representation of sound and such problems as speaker recognition and speech synthesis. Like other problems like speech recognition and non-speech audio problems, we will not consider in details today, but I hope that you will be able to read research on these topics yourself like after some introduction, after today's introduction. Okay, let's start. Firstly, I'd like to explain what is the nature of sound, and there is very nice video on the YouTube with a good visualization. So I propose to watch this 5-minute video just to refresh your knowledge about the nature of sound. So, sorry, just a second. If the sound will be not loud, please interrupt me. So do you see the transmission of sound video?
Yes, yes.
Okay, great. So let's start.
Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. There are mainly two types of waves, transverse wave and longitudinal wave. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves? This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky, while Dr. Zook is pulling its other end towards himself, and then pushing it towards Emily. Watch closely, and you will notice that some of the coils crowd close together, and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Sound waves travel in all directions. Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo. Bouncing back of sound is purposefully used in detecting depth of seabeds. That's amazing, isn't it? Summary. Every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. There are two types of waves, transverse wave and longitudinal wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Bouncing back of sound is called echo.
Dear fellow scholars, this is 2-minute papers with Karo Jonai Fahir. This work is about creating an AI that can perform audio-visual
transmission of sound.
Okay, so this is all for the video, and I'll return to the presentation. Okay, so we understood that sound wave is a longitudinal wave, and we hear when the sound energy reaches our ears, and the speed is described with the frequency. So let's consider which task can be solved using audio or voice signals. So let's start with a more simple task like speaker recognition. So what is speaker recognition? Let's distinguish first between speaker and speech recognition. If we have input voice signal and we want to know the identity of the speaker or some characteristic of this speaker like emotion or gender, we call this task like speaker recognition. If we want to extract some linguistical features, we talk about like speech recognition or like automatic speech recognition. Also, we can separate like language recognition task when we determine the language of the input audio signal. So speaker recognition task can be considered as a particular, like speaker ID can be considered as particular task of biometrics. Like, what does it mean? Like each speaker has its own voice, and the footprint of its voice is unique. So if we combine it with such biometrics as fingerprint or face or like hand geometry, that can describe a person in a unique way. And so that can be used for security technologies. For example, we can combine voice recognition technology with their passwords, with some key cards, and all these technologies will produce like security system. So when this is useful, so there are several applications like bank transactions that are made by phone, for example, or if we want to get remote access to some databases using voice, or if we need to control some access. So there are a lot of applications that can be very helpful in real life, but that are not used widely in modern days. And so this area is quite a hot topic. And many IT companies, they are interested in developing these techniques like speaker recognition. So let's consider how the speaker recognition tasks can be separated. So they can be like text dependent and text independent. So text dependent means that having an audio signal, we also know a text that corresponds to this audio signal. And that means that we can extract additional information from the text, and we can obtain more safe system. However, today we will concentrate more on text-independent tasks. They are more challenging because we don't have a text on which we can be conditioned. So we will assume that we have only audio as an input. So which speaker recognition tasks we can consider? The first one is identification. So this is the task that answers to the question like, whose voice is this? Like if you have like a base of like many, for example, American speakers, and you want to understand if our given voice signal belongs to one of these speakers, you solve like identification task. So another important task is verification. So verification task, this is like binary classification task that says you whether a given audio belongs to this person or not. And verification task is a task. It is a part of our security system. So another one is diarization. So assume you have an audio signal, very long audio signal, and you need to understand at which period of time which speaker speaks. So firstly, you have to perform segmentation task, and then clustering task to figure out which segments belong to which speaker. So this is diarization task. Also, if you're interested only in tracking one speaker, you can consider tracking task when you just classify each segment as a segment that belongs to a given speaker or a segment which is not belong to a given speaker. So let's see more close how we can work with audio signals. So like in all machine learning models, before applying such classificator, or detector or other algorithm, we need to extract features. So how we extract features from the voice? So voice is a multi-level, described with multi-level features. We have high-level features like pronunciation or diction, also derived features like rhythm, speed, and there are spectrum derived features. What that means, our heart has a specific construction, and this construction is unique for every speaker, and this construction, it's influence the value of spectrum features. We will consider later, in more details, how they're constructed. But these low-level features, they can be derived from the audio, and in many applications, these features, only these features are used to construct predictive models. But of course, we would like our models are to be to exploit all the features, but that is not so easy to do, and there are recent works that try to perform some voice conversion tasks by exploiting prosody of the speaker, but this is out of our scope today. Okay, let's consider how the features are constructed. So we will divide our two big groups of features, like raw audio is just a raw signal. So raw signal means that at each time point we have a value of energy, and this is called raw signal, and this is depicted on the first image on the slide. However, this signal might be not very convenient to use as input feature because the time dimension has a lot of sample points. So we can have like thousands of points like per second, and this is quite a lot. So in this situation, like spectrum-derived features are very useful. So let's consider construction of like spectrograms, Mel spectrograms, and Mel frequency substrate coefficients. So let's start with the spectrogram. Like, assume we have like our time signal, and if we cut a frame from this audio signal, we can perform Fourier transform with it. And like on the left picture of the slide, you can see a simple example. Like assume we have a signal that is a sum of 3 like sine waves. Then when you perform like Fourier transform, like in frequency domain, you will obtain a graph that has like 3 maximum that correspond to frequencies of cosine waves. So if we have more complicated signals, we will obtain like more complicated graph in frequency domain. So let's construct spectrogram now. So what is spectrogram? Spectrogram is a frequency time representation of our signal. So yes, we have input signal, we cut some time segment from it, and then we perform like Fourier transform with this segment. Yeah, worth noting that before performing Fourier transform, we also apply some smoothing, namely we attenuate the values near the edges, like the beginning and the end of the interval. This is done like to decrease the artifacts that arise because of like our procedure that like sequentially takes the time segments, and like when they are connected, they could arise some artifacts. So we want like to eliminate that. Okay, so we perform Fourier transform and we obtain like our plot in a frequency domain. So this is our like, sub-image C. So we have like frequency domain. And now we want to convert this plot to one column of the spectrogram. So spectrogram will have like this column, this like one time point that corresponds to our like time segment, and like the frequency values, they correspond to the x axis from our sub-image C, and the color of this column corresponds to the energy hour. Yeah, just to be more precise, if this spectrogram is written as a function of time t and frequency w, then we can say that like one cell of this spectrogram is a short time Fourier transform, like to the power of 2, like at points t and w. So if you have any questions, you can interrupt me, because it's quite an important presentation that will be used later. If everything clear, okay, let's go further. So the thing is that human, they don't distinguish like all frequencies in the same way. Like, for example, we can distinguish very well like the sounds that has a low value, like represented with a small number of hertz, but we can distinguish very well like higher sounds. So that means that we are less sensitive when we try to distinguish not like low frequencies, and that's why like special units were introduced. So namely, instead of hertz, it was proposed to use mels, and mel means that like two values that are equally distant in like mel scale, they have same perceptual distance like for human. Okay, let me provide an example. Like, assume you have a signal that is characterized by like 100 hertz, and signal that is characterized by 150 hertz. So there is like different 50 hertz. And then let's consider 1000 and 1050 hertz signals. So you feel the difference between the first pair much better than the difference between the second pair. And actually this is a problem with the human perception of the sound. So when we talk about mels, if you consider like sound that is characterized like by 100 and 150 and 500 and 550 mels. So you feel the difference like equally. So hope this example explained a bit the motivation of introducing like mels and mel scale. So we already discussed that we can represent our signal in time as a time frequency representation. And now we want to represent frequency axis, like in an axis that is more suitable for our like, perceptual system. And that is why we will construct a MEL spectrogram. So how we will do that? We will build filter bank, like MEL scaled filter bank that aggregate and somehow the energy across the frequency domain. So as you can see from the picture on the right, there are different intervals, and the lower the frequency, like the narrower the interval. So that means that exactly shows that like when the frequency of the signal is lower, we need like more functions to describe the signal, because we can recognize like low frequencies very well. So yeah, how we obtain this representation with a good like frequency scale, like perceptual friendly frequency scale. So actually we just apply MEL filter banks to our spectrogram. So this is just a scheme that demonstrates that having like a spectrogram, we apply MEL filter banks, and then we obtain MEL spectrogram. Like from like mathematical point of view, you can think about that like you had like spectrogram matrix that has some number of beams that which has a size. Okay, let's go back. So there's a spectrogram. It has like time axis and frequency axis. So, and then we convert it to MEL spectrogram. MEL spectrogram has the same number of time dimensions, but it has lower number of like frequency bits. And so you can think about obtaining MEL spectrogram as like multiplying spectrogram by matrix. Okay, so now we know how to construct like time frequency representation that is convenient for our perceptual system. However, that representation still is not very compact, and there is another characteristic that is very useful for that has been very useful maybe 5 years ago in different speaker recognition tasks, and it's called like mel frequency substrate coefficients. And to obtain this value, we should compute the logarithm of mel spectrogram and perform discrete cosine transform on top of it. So we obtain like spectrum of spectrum. And the thing is that like this representation is very compact. Just for example, if your initial spectrogram could have like 512 beams, frequency beams, and like 500 time grid points, so your MFCC features can be represented like only with 30 values. So this is very compact representation, and the good thing about that is like unique feature for a person. So here we will consider like a standard model for speaker recognition that was used like 10 years ago, and it was based on MFCC features. So having a speech segment, we extract the mel frequency substrate coefficients, and then we use like the following procedure. So here we assume that like before having some test audio, we were able to construct some universal background model. And what is it? So like each audio segment, we assume that it can be represented, it can be described like a sample from a Gaussian mixture model. And actually this universal background model, this is like a Gaussian mixture model, and it has like capital M components. And these components, we already know, we trained our model for many samples. And given like a new sample, we perform like map adaptations. So we obtain like speaker model. So you can look to the graph at the bottom, at like right bottom, and so we have our universal background model. It is like orange with orange components, and then we like add samples of like new training data, and we obtain like a new values for means of Gaussian components that correspond to the speaker model. So we have like two we have like two models like universal background and speaker, and then to solve like speaker verification task, we just look for the fraction of these two values, and like if it's exceed the given threshold, then we either like accept or we have either accept decision or like reject decision. So the speaker is verified or not. Like that was very useful model, and after it was modified with a model that used like SVM on top of the pipeline. And the difference is that the means of the components, they were proposed to be stacked like in a one big vector that was used to perform classification, and so we could like train this model. And actually this method was like state of the art for like many years, and I think recently it was also used. I heard maybe 2 years ago that in Sberbank they used this model. Maybe Alexei knows more about that, and yeah, but I think now they're switching to some narrow network pipelines. So okay, so sorry, they use not super vectors, but a bit modified version that allows us to reduce the dimension of super vector to some small representation called I-vectors. So this model was very popular and has been used by like many in many practical institutions. So the ways how we obtain these small vector, they can be different, but that is not so important at this moment. So let's move further. So what is important that like at all stages of this pipeline, we can perform substitution of each step with a narrow network. And the thing is that there were a lot of papers that substitute one of the parts of this pipeline with a narrow network to achieve more automatically constructed models and to achieve some better results. Yeah, so the goal was to replace all these stages with a one end-to-end model. And now I want to make an overview of such end-to-end model called Deep Speaker. This is a pipeline proposed by Baidu. And it looks as follows. So we have input signals, so mini batch of input signals, and then we perform then we extract spectrum features. Then there is like some neural network which obtain our spectrum features as input and outputs some hidden features that are further processed using special layers that were proposed in this paper. So, how spectrum features were extracted? So, in a very similar way that was described several slides ago, like having an input signal, we divide it into frames. We perform some smoothing like with window. Then we perform Fourier transform. Here they apply some filtering just to through out like very high frequencies that usually correspond to some noise, not to the voice. So after that, they construct feature metrics that included male frequency substrate coefficients. And so this is input representation to the neural network. And as a neural network, they considered different architectures. We will see the results for them in the next slides. Oh yeah, just a few words about layers that can be used, that were used like in the pipeline, like average layer that just average all feature dimensions over time axis, and some affine and normalization layers. And the whole model was trained with a triplet loss. So having like a sample, like enter, and also like positive and negative example. So the model tried to minimize the distance between positive and enter samples and maximize the distance between negative and enter samples. And as a metrics, so this model has been tested for both verification and identification tasks. For identification task, accuracy metric has been used. For verification task, it was used so-called equal error rate metric. And the thing is that like the lower this EER metric, the higher the accuracy of the like verification system. So actually this matrix, it indicates that the proportion of false acceptance is equal to the proportion of like false rejections. So yeah, the lower the better. So let's see the results. Here are two tables. Both are for text-independent speaker recognition tasks. So the first column describes the model that has been used, and here this deep speaker proposed model was compared with iVector baseline. So DNN iVector means that like some parts of the pipeline we described, we considered before, were replaced with neural network models. And so as you can see from the tables that the proposed deep speaker pipeline outperformed the iVector-based models for both like Mandarinian language and for like English language. And also you can see that this model have been tested for different laws, like for softmax and for triplet, and also like for some hybrid training procedure when they pre-train the model using softmax laws and then just tune with triplet laws. And like these are like combination from Mandarinian language provided like the best result. Yeah, so this is like verification that neural network-based models can provide good embeddings for the speaker. Okay, now let's switch to another class of models that are very important nowadays, especially like speech synthesis models. So why they are important and what they do. Speech synthesis model generates audio from some sequence of symbols. That can be text, that can be some representations like Mel spectrogram or raw audio. The thing is, we have an audio signal as output. So when these models are useful in, for example, in voice assistants, like Siri or Amazon Alexa or Yandex Lisa, and also it can be very helpful for the people with their like disabilities and another like area where they're useful is like personalization. It's not like cool to have one voice for like all people. Like for example, if you want to like I think many people would like to have like their own automatic voice that could like read books with their personalized voice or like sing songs, etc. So this personalization issue actually is quite important for everyday life, like for the convenience and like for yeah, just to like have better like, assistance. And here I mentioned like main papers that correspond to speech synthesis. Actually, there are many of them, but mostly they're based of these architectures. So like there is like deep voice model. It was proposed by Baidu, and then so they also published Deep Voice 2 and Deep Voice 3 models. So in parallel, like Google proposed like Tekatron model, and then Tekatron 2 appeared. And also Google DeepMind, they were working on WaveNet and different types of WaveNet-based models. So let's consider in a bit more details. So the first one is deep voice. So a deep voice pipeline includes like 4 main models that trains like separately, not in an end-to-end way. So they include like Graphem to phoneme model, like the model that estimates the phoneme duration, also the model that estimates fundamental frequency, and the model that perform the waveform synthesis. So here on this slide, like on the top, you can see how the training has been performed, and like on the bottom, the diagram for inference is depicted. So, for example, for inference, you have some text, you have input text, and so this text is like divided for some like smaller parts, and like a special model, it converts this like text parts to some some audio like segments, like to phonemes. So phonemes, they represent some sounds or a combination of sounds, and this phoneme dictionary, this is the part of the model that was like handcrafted. So you got the phonemes, and having them, you predict like duration and fundamental frequency. And having these parameters, like audio synthesis is performed. So how this audio synthesis is performed? Actually, this is like a part that is done for so-called vocoders. So vocoders generate audio signal. So for example, yeah, and they can be derived for like 3 groups, like parametric vocoders that take as input some parameters as like fundamental frequency or some like spectral statistics, and yeah, and generate audio. And here I listed like well-known parametric vocoders. So second algorithm is a Griffin-Lim algorithm. This is quite an old one. I think it's from 1970s or 80s, but it works very well. It's usually quite useful for validation experiments, for test experiments. And what it does, like having a spectrogram, it reconstructs an audio. Yeah, and like each like audio signal it can be it described by its like amplitude and also by the phase. And when we compute like spectrogram or Mel spectrogram, we lose this information about like complex part of the signal that is described with the phase. And what the Griffin-Lim algorithm does, actually, it iteratively updates the phase coefficients and end up with their audio approximation that sounds very well. Actually, for like true spectrograms, it's very difficult to distinguish like reconstructed signal from the like initial one, from the original one. However, this algorithm has a drawback. Like it can have iron artifacts in an audio. So to fix these issues, in recent years, several neural network-based vocoders have been proposed. So I mentioned here the most popular ones, and we will consider WaveNet in this presentation. Yes, so to conclude, how you synthesize our speech. So you have some input, you have like two options. Like you have some input features like text, for example, and you have some model that generates spectrogram. And then you put this spectrogram to Griffin-Lim algorithm and obtain the audio signal. And yeah, this in this case, you need to train only the model that generates spectrogram, because Griffin-Lim doesn't require any like training of any parameter training. So the second option is like you generate like your spectrogram, like or Mel spectrogram, and put it to like neural network based vocoder. Actually, you put it to like to another neural network. And the thing is that the neural network-based vocoders, they can be, like in some models, they can be trained separately. Okay, so let's consider in more details WaveNet model. This is an autoregressive model, and it means that okay, if you want to predict the sequence value at time like t+1, you have to take into account the values from the previous time steps. And in terms of like probabilities, you can write the regressive model as like in the first row, as it is written in the first row. For the practical cases, like you can choose like the value m that means like how far to the past you should look when you like predict the distribution and the time t. And here the lambda, it can describe any features that you would like to use other like conditioning. So it can be like speaker ID or some text embedding, like any additional information you want to add. And this conditioning, it can be like global, like same for each time like point, or it can be also like local if it's like changes with time. And to train the pipeline, so the following loss function is used, but to evaluate the quality of the trained model, actually usually another metric is applied, and it's called mean opinion score. And actually it's quite subjective metric, because what is done, so you just ask people to evaluate the generated audio with score from like 1 to 5. And so you just collect statistics with these human scores and like provide the results. And yeah, the problem is that like different papers, they use different people to evaluate the score, and actually it's usually difficult to repeat the results of the concrete paper, because it's difficult to get the same people that evaluate the mean opinion score. Okay, let's look at the architecture of WaveNet. WaveNet works with raw audio representation. And it means that we have our signal representation in time, and we work directly with time representation. We don't convert it to like some spectrum representations first. And the novelty that was proposed in this paper is dilated convolutions. What does that mean? That's like firstly you like convolved like neighboring time points, yeah, samples, and then you like when you perform like second convolution, you convolve like the samples that are that have like another sample between them. And so with each additional layer, you like increase the distance between these samples. And such convolutions, they allow to use like long they allow to use a lot of like information in terms of how far you can like look back, and performance not so slow as if you considered like a standard convolutions. So you can imagine that if you compute like each arrow that is depicted on this picture, like both like black ones and like gray ones, that would take like much more time than to compute only like black arrows. So yeah, this was introduced in WaveNet architecture. And actually the architecture itself, it contains several stacked blocks. When you predict the model, so you just generate samples in an autoregressive way. And the thing is that it's not very effective. It's quite it's quite slow. So if you want to add some conditioning while you generate the audio, for example, you want the audio sounds like your friend, then you can use speaker embedding. So here it is depicted with vector H, and you just add this to like difference to the different levels of the architecture. Yeah, as I said, like when you perform like sampling, so WaveNet does that not very efficiently, because it generates like each sample in autoregressive manner. And the paper Parallel WaveNet proposes how to perform this inference more efficiently. And they introduced like a student model that generates samples during like inference. And they used pre-trained WaveNet to guide this student WaveNet during training. So they used like teacher-student paradigm when they trained this model. And the thing is that they used a type of normalizing flows to speed up the generation. And the follow-up papers of the parallel WaveNet that were mentioned in the slide at the beginning of speech synthesis, like ClariNet or Flow WaveNet, actually they are just some modifications of this model, but they use like different type of normalizing flows. Okay, so let's switch to another model like Tekatron. So Tekatron, it works like in it can be trained in end-to-end manner, and that differs it from the deep voice model that we considered before, and that had like 4 different networks that should be trained. And so how Tekatron works, we have some character like embeddings, and so they are going through some preprocessing network. And then there are like several stacked units that are used to to compute some attention map, and during the sequence generation, like sec-to-sec model is used, and so what is generated? We generate like a spectrogram. So in contrast, like to wavenets, so here we generate like a spectrogram, not the raw features. And after this spectrogram is generated, so Griffin-Lim algorithm is applied as a vocoder. So yeah, actually we can apply any other vocoder we want, but yeah, Griffin-Lim is the simplest one. So we considered like main models on which like many modern papers are based, like deep voice and Tekatron, and also we considered like WaveNet that can be used at their good vocoder that works better than just simple Griffin-Lim algorithm. And there are modifications like Deep Voice 2 that actually allows to perform multi-speaker synthesis by exploiting like speaker embeddings inside the pipeline. So there is like a Deep Voice 3 that in terms of quality performs like Tekatron, but maybe 10 times faster. And also there is like a Tekatron 2 model that that generates like MEL spectrograms and use WaveNet based vocoder, and it performs better than the like Tekatron, the previous Tekatron. Yeah, and I want to say that there are very interesting models also from NVIDIA company. I haven't mentioned them here. but yeah, you can Google, for example, Mellotron. This is like a speech synthesis model that allows you also to control some speaker features like rhythm, for example, or like frequency, like fundamental frequency. And yeah, the thing is, like recently, there are many papers that try to propose models that can be easily adapted for different user features, and not only like to main like user properties like rhythm or fundamental frequency, but also they try to mimic such some defects of speech, because different like defects of speech. This is what this is like very unique for like every speaker, and yeah, if we can like easily synthesize speech with these like features, that would be really cool. Okay, and just one of the last slides, I wanted to mention that the models we considered for speaker recognition actually can be applied for other like audio classification tasks with some modifications. For example, we can solve like environmental sound classification if we have a lot of city sounds, or if we want to classify birds sounds, also music genre classification. In terms of synthesis, there are popular problems like audio texture synthesis. Like if you want either to invent some new sound or just to add background to your like, generated speech. So the example could be like wind blowing, or the sound of forest. And also, yeah, very interesting like audio tasks, either like music translation. It means that if you have some audio like played by violin, for example, you can train the model that converts this instrument to this audio to a piano audio, and there are models that can solve this task quite successfully. Yeah, and many other interesting problems. And of course, yeah, big class of models. I haven't covered today's like automatic speech recognition. Yeah, but I encourage you to also study them, because like in a modern conversational system, you usually have like three main building blocks, like speech recognition, when you convert like audio to text, and some language like model processing unit that like generates like answers or like dialogue, and then like speech generation or speech synthesis model. So today we considered like this like speech synthesis model of conversational AI like system. And here I got the reference slide. I mentioned some study materials that I found useful. I will send the presentation, so you will be able to click all these links. Yeah. And yeah, this is all from my side. If you have any questions, please ask. I will be happy to answer.
Yulia, thank you very much for the presentation. Does anyone have questions on this? Okay, it seems like no questions today. Thank you one more time. And the record and the presentation will be available later from us. And okay, I think I can pass the word to Rodrigo if he has something to add to the lecture and to the overall running of the course.
Yes, thank you, Alexei, and thank you, Julia, for the presentation. Very insightful. I wanted to add that we'll have a material for the seminar, but it will be only available on Notion, so it will be released so later today. And so given that we have basically just until Friday for the final presentations, then it is very important that you focus on that. So we do not plan to have any more quizzes. By now we have quite a few ones, and you should focus on the presentation. For this, the mechanics it is, you already have it from the Notion page, from Canvas, but basically you have until Thursday to submit all the materials. And on Friday, we'll be reproducing the videos. Everyone has to attend. There'll be a Q&A session. We will ask you questions about your presentation and so on. So everyone must participate during this session and be ready to answer individual questions about your work. So that's everything from my side, Alexei. So I don't know if you have anything else to add.
Okay, seems like no questions. And okay, so this is the end for today. Thank you very much for attending the presentation and for listening to Julia. And I would be happy to listen to you on Friday. And also know that Dmitry Yarotsky will help me with the assessment of the project as well as Rodrigo. So good luck for Friday and
okay,
bye.
bye.
Bye, everyone.